What's up guys, I just came back from vacation and in this video I'm covering efficient visual pre-training with contrastive detection, or DetCon for short, by the DeepMind team. But before I even dig into the paper, I want to announce a couple of news I have for you. So the first news is I just created a brand new Discord server, so that means we'll be able to drive the engagement in this community so much more, and you'll be able to get answers to your questions without relying on me answering every single question on YouTube and everything and all the goodies that Discord brings with it. Also, you'll be able to suggest the repos I should do the code walkthroughs off, because I want to be more bullish going forward, doing those like hands-on coding videos, and hopefully you'll find that useful. Anyways, sign up for the Discord. I'll just link it down in the description, so check it out. So the second news is I'm creating a new monthly AI newsletter where I'm gonna cover like the hottest, the latest and greatest things that happened in the field of AI on a monthly basis, and I'm gonna keep it high level, so that means it will be suitable for engineers, researchers, and entrepreneurs as well. So compared to these videos where I'm in a zoom-in state in a particular paper, there I'm gonna give you a brief understanding of what happened over the last month. If you want to just quickly catch up with the things that happened, that's what this newsletter is gonna be all about. And again, just sign up for the newsletter. I'm gonna link it down in the description. So having said that, let me jump back into the paper and see what's happening here. So DetCon is another self-supervised learning paper, and it's just like basically piggybacks off of BYOL and SimCLR research, with additional idea of including the segmentation mask information in order to create those representations. Okay, so let's start from the main motivation. Self-supervised pre-training has been shown to yield powerful representation for transfer learning. These performance gains come at a large computational cost. However, with state-of-the-art methods requiring an order of magnitude more computation than supervised pre-training. So the trade-off here is fairly clear. So on one hand, you have you don't need expensive labeling annotation teams, so you can kind of save up on the cost there. But on the other hand, you have to invest in more computational, so your infrastructure, your compute will rise with some of the older methods. So that's the trade-off you kind of have to accept, and you're still not going to approach the representations that you get from having from applying a supervised paradigm. But SSL is definitely getting closer, and this paper is just in the right direction, I'd say. Okay, so as you can see here, on the x-axis we have a number of epochs on ImageNet. So we're training these different methods on ImageNet, and they are then fine-tuning them on COCO and kind of reporting the detection accuracy. And you can see that using SimCLR, which is one of the older self-supervised learning methods, we can see that the performance is nowhere near as good as with a supervised method. And then we can see that this novel method, so DetCon, actually surpasses even the supervised method in 5x less computations. You need around 200 epochs instead of 1,000 epochs to achieve higher accuracy on the COCO detection task. So I already mentioned that, or I think I mentioned that basically this paper piggybacks off of SimCLR and BYOL, and I'm going to dig a bit deeper into those two. But first of all, let me kind of show you how this whole method works. So here it is, and if you read any of those older papers like MoCo, SimCLR, BYOL, whatever, you'll be fairly familiar with this similar pipeline. So what we do is we have an image, and then we do two different augmentations. So we'll have something like T, augmentation T, and augmentation T prime. And as you can see here, so here we had some crop, the elephant is now cropped and zoomed in, and here we had some other types of augmentations. So what we do next is we just apply encoder, which is your regular CNN. They've used ResNet across this paper to get these convolutional features. So this here is just the spatial extent of the features, and there is a third dimension here not shown, which can be maybe 1K dimensions there. Okay, so now the important thing to notice here is that they are using these segmentation masks. And that's the difference compared to BYOL. That's the difference compared to other SSL methods that we've seen so far. And we're gonna see how they actually calculate the masks. But for now, just let's treat that as a black box. And now the whole idea of the paper is the following. So you have an elephant here, as you can see it here. And you can see these red dots represent the feature vectors that correspond to that spatial extent of the image. Here we have more red dots because the elephant occupies nearly the whole image. And so now, in order to form representations, what they do is they take those masks, so they take the information from the mask. So with that, like segmentation mask information, they can pull exactly those feature vectors which correspond to that red mask or to the elephant mask. And so that means effectively you'll take these, like as I said, these are maybe 1K dimensional feature vectors. You'll just take them and you'll do average over all of those 5 vectors in this case here, or whatever the number of red vectors here is, and that's how you get the final representation here. Okay, you do the same procedure for all of the other masks. So because this image had different augmentations compared to this one, here we still have this yellow object, whatever this is, like a human. So that means we have that vector here, whereas we don't have it here. And now the whole idea is the following. We just want to make sure that the red vectors have a representation such that they are closer together in the vector space, whereas we want to make sure to push away the red from the blue vectors here. And again, we want to pull the blue vectors, and we want to, because we only have yellow here but we don't have yellow here, we want to just push away the blue vector and the red vector. So that's the main idea. Using these segmentation masks, they have a richer learning signal, and they are able to do this fine-grained push and pull standard contrastive learning scheme. Okay, so let's dig into some formulas here to make this a bit clearer. So here is just a formulaic representation of the thing I just explained. So basically, M is your segmentation mask, and it's going to be a binary mask. So basically, what M will do is the following. So M will be something like this. So for a red mask, it's going to have ones here. So these will be ones, okay? And all of the other ones will be zeros. So these will be zeros, okay? And now, as you can see here, so H is just a feature vector that came from the CNN. So that means, so these here are H vectors, okay? So, and as you can see, for every particular slot, so for this one, the mask, this binary mask, will decide whether we want to use that feature vector behind it, so whether we want to use the feature vector or not, okay? And that's simply described here as this. So when M equals 1, that means that the mask is active. That means we're going to use that feature vector and kind of sum them up and then divide by the number of like active units. So let me kind of clarify that. So here we have 5 times 1, so that's going to be 5. So that means we're going to take these 5 vectors, add them together and divide by 5, which is basically what I already explained, and that's average pooling across those vectors. So that's how we form the representations. So that's this part. Now the second part is, as I said, they're piggybacking off of BYOL and SimCLR, and so in order to like having formed those HM representations, we now need to form these VM representations before we actually apply this contrastive detection objective, which I'll explain in a second. Okay, so again, these here are only HMs, and now we have to form VMs before we actually apply the objective. And now I'm going to briefly explain. So as I said, these formulas correspond to SimCLR, and these ones here correspond to BYOL. And then for now, let's just treat it as a black box. We somehow calculate these VMs, and what we do next up is, as I said, we do this push and pull, this pulling and pushing away of these feature vectors. So once we have those VMs, we can then do the thing I just explained pictorially here. So this pushing away of different of vectors that correspond to different objects and pulling together the vectors that correspond to the same object in the image. So this is just formulaically described here. Basically, as you can see, so VM and this VM prime just correspond to the same mask. So M is, for example, red mask, and prime just means different augmentation. So this means basically the following. So let's say this is, just for the sake of argument, this is now VM. Just ignore it. It's actually HM, but let's say we pre-process it using this BYOL or SimCLR, and now we have VM here. So what we want to do is, so this will be the VM, and we want to make sure that this one is as close as possible to this one. So those are two vectors. We want to make sure that the dot product between those two is super high. That means they are similar. On the other hand, we want to make sure that this so this red vector is pushed away from this blue vector, and same for the other vectors. So that's the whole idea, and that's kind of captured in this formula here. So we want to make sure that the vectors corresponding to the same mask, so for example the red mask, the elephant mask, are similar, where we want to make sure that these negative ones are pushed away. So that means this will get negative. That means exponential function raised to a big negative number goes to 0. So this will roughly go to 0, let's say, and that means that's how this loss will get minimized, because minus log looks something like this. So this is your minus log function, which means you want to push this value here to 1, and that's how the loss is minimized. And by doing that, so that's a numerical intuition. But what happens in that process is that, as I said, the red vectors, or the vectors corresponding to the same mask, get clustered together, whereas all of the other vectors get kind of like pushed away from each other. And that's the whole idea. Nothing fancy there. Now, briefly, before I start like giving you some overview of BYOL and SimCLR, let me show you the segmentation masks and what I've used. So obviously, it wouldn't make sense to have a self-supervised learning method if you presuppose that you have semantic segmentation masks, because those require obviously labeling from humans. So what I've done is they tried a couple of heuristics. So some of these heuristics for calculating the segmentation masks are super simple and like primitive, like this one's the spatial heuristic, where you basically cluster and assume that the neighboring pixels belong to a specific object. And so they tried this one. They also tried this FH algorithm heuristic, this MCG, and those are not that important. Basically, they're just some more advanced heuristics compared to the spatial heuristic, obviously. And finally, they used human annotated segmentation masks. They later showed some intuitive results that having better segmentation masks like this one actually improved the method by quite a lot. Okay, so those are the segmentation masks. Now, let me slowly dig into these BYOL and SimCLR methods. Again, the ideas of many of these self-supervised learning papers are fairly similar. So what I do here again is you have an image, and you apply two different distinct augmentations, and that's how you get view T and view T prime of the same image. So that would be something like this, right? So like you had an elephant, this picture here, and you get two different images. So that's the idea. Okay, so once you have those, what BYOL does is it does not use negative samples. So that was the novel thing that BYOL did, and it managed to actually create high quality representations without them collapsing. And I'm gonna slowly digest what that means, but stick with me for now. So as I said, you have a view here, you apply an encoder, which is again usually your CNN, you get some representation, then they have this G theta, which is basically like a shallow MLP network, which is like a projection head. You get this projection representation, and then they apply additionally this additional MLP, which actually was one of the important ingredients to avoid the collapse. So this asymmetry between the upper branch and the lower branch was important fact in the important piece of information in BYOL. Okay, so on the other hand, the lower branch is just constructed basically from the upper branch by using something called exponentially moving average. So that means you just take snapshots of the upper network in time, and you use the exponential logic to kind of average those out, and that's how you form these F psi, or whatever this Greek letter is pronounced like. And then you kind of propagate, and you get this final representation, and the whole goal will be to, after you do some L2 normalization, so whatever this vector is, let's call it V, what they do is they first normalize it using L2, so they just find the L2 of that vector, they normalize it by dividing it by the L2 norm, And then they want to make sure that these two representations, basically by doing this MSE loss, mean square error, they want to ensure that these vectors are the same. And so intuitively what that computational thing does is it forces the network to learn how to abstract the important parts of the image. So no matter the augmentations, you want to extract something that's inherently present in those images, and by learning that you learn valuable representations which are agnostic to different augmentations. You can still capture and understand what's in the image. So that's the whole point of BYOL. And they showed empirically that by doing this they avoid the collapse. So why would the collapse happen? Well, it's simple. Like the easiest, most trivial way to kind of make sure you are minimizing this loss function is to always output a constant representation. So no matter the views, so give me an image, whatever the image is, whatever the augmentations are, after you pass them through f theta, you'll get some constant representation. Let's call it like VC, like constant vector. And you get VC here as well. And that means basically, not here, but like here at the output, you get constant representations. And that means that this is basically approaching zero without you learning any interesting representations. So BYOL avoided this collapse, and back then when the paper came out, like they didn't have like a super strong theoretical understanding of why that is, but some recent paper actually kind of explained this a bit better. I forgot the name of the paper, but yeah. Now SimCLR is similar but different. It does so. I'd say one of the main differences is that it uses negative sampling. So what SimCLR does is the following. Again, we have T and T prime, so we apply different augmentations to the same image, and this time they apply the same encoder in both branches, and then they apply the same projection head in both branches. And now the whole idea here is to make sure that the augmentations belonging to the same image are similar, so those representations are close together in the vector space, whereas representations from different images are further away from each other. So let me try and kind of visualize that a little bit. So this is your image, and you have a batch of images. So you apply the first augmentation and you get image T1, and you apply the second augmentation to the same image, you get T1 prime. Now you have a second image, and you again apply augmentation and you get image T2 and you get T2 prime. And you do this obviously n times because you have n images in your batch. And now the whole point will be the following. You take the representation you get from this T1 image after passing it through F and G, and you want to make sure that that representation is close to this one because they belong to the same image. And then you want to make sure that it's far away from these representations, from this one as well. You want to push it away from those representations. And the same for every single image in the batch. You're gonna push them away, and the only thing that's getting pulled together are those two images here. So that's the whole idea of SimCLR. So that's just kind of formulaically showed here. You basically have, as I said, so similarity, usually dot product between those representations. There's some temperature coefficient, but the whole point at the end is to kind of do what I showed you here is just symbolic representation of the thing I just explained to you here. Okay, having understand that, let me now go back to the method, and here we are. So again, here's the SimCLR method. So you can now see that HM is the representation that comes from the F, so from the encoder, and then they just apply the projection head, and that's it. That's everything you need to form representation for SimCLR, and then you apply this novel objective function. To get representations for BYOL, they additionally just add this head which I mentioned, which gives you this asymmetry in the pipeline, and obviously they also use this network. So that's the network form from the exponential moving average. Okay, so now you can kind of hopefully ground these formulas to the BYOL and SimCLR papers. And again, once you have the representations, those VMs and VM primes, you can do the logic I explained a couple of minutes ago, where you're forcing the vectors for where you're forcing the vectors that correspond to the same masks to be closer together, whereas you're pushing away the vectors belonging to different masks. And whereas masks correspond hopefully to different objects, and that depends on the quality of your segmentation masks. And they did some ablations on how those different, how these different algorithms affect the performance of the method, and we'll see that in a couple minutes. Okay, let's see the results finally of this DetCon method. And as you can see here, so having pre-trained it on ImageNet and then fine-tuned it on different tasks like COCO instance segmentation, Pascal semantic segmentation, Cityscapes semantic segmentation, and NYU depth estimation. You can see in all of these 4 tasks, which are fairly different, like the DetCon method performs way better compared to the supervised and SimCLR baselines. So I think let's focus for now on one chart, and then I'll tell you some interesting things I see here. So first things first is you can see here that SimCLR, after a certain amount of given enough computation, like surpasses the performance of supervised like paradigm. And that's something we saw in the beginning of this paper. So given enough compute, that's a trade-off. You're gonna eventually get there, but you need a bunch of compute, right? Whereas here you can see, focusing on DetCon, that like after only 200 epochs, you're already better compared to these 2 paradigms, and you have better performance. Okay, so the same thing applies pretty much for all of the other tasks. So I won't be digging into every single chart here, but the interesting thing here to notice is that supervised like paradigm completely fails for these 2 tasks, like depth estimation and semantic segmentation, which means that the supervised pre-training on ImageNet is not informative enough. So the features are not informative enough for these particular tasks, whereas SimCLR and DetCon seem to generalize better to different tasks, which is another plus and bonus point for applying SSL because you get more generalization out of the method. Okay. I'll skip this table. It just has like a numeric representation of the thing we just saw here. So basically the main point they're trying to drive here is that with 10x less computation, they can achieve performance that's much better than all of the other baselines. So here you can see with only approximately 100 epochs, it's already better than SimCLR, which is way better than supervised learning on this Cityscapes semantic segmentation task. So that's the whole point. Okay, going forward, let's see what else is there. Okay, here they compare like DetCon again against various different like baselines, not only BYOL and SimCLR, but also MoCo, supervised, SWAV, and other methods, and they just showed that it consistently outperforms all of those baselines. So one thing they've worried about is that maybe scaling the number of parameters will kind of give us something qualitatively different behavior with DetCon compared to the previous baselines, and this basically just confirms that this method does scale with scale, and like the performance does not change, and it still outperforms. So DetCon, the blue one, still outperforms all of the other baselines like BYOL, SimCLR, and supervised baseline on these COCO detection and COCO instance segmentation tasks. Okay. Moving further, they even showed that this recently published method SEER, which used billion images for pre-training and has way more parameters, it's still like the DetCon outperforms those methods, which is a nice result. And they kind of mentioned that it's not super comparable because SEER uses the data that SEER uses is way more noisy. It's kind of not a fair comparison, but still it's an impressive result. Okay, let's see what else interesting is here. They showed how using different segmentation masks, so different heuristics, which I briefly described before, improves and changes the performance. So as you can see here, using those spatial like heuristics, so that's this one. Let me just go briefly up there. So this is the spatial heuristic, and here we have, so this upper here is 1 by 1, here we have 2 by 2 grid, and here we have 4 by 4, okay? So that will hopefully help you understand this chart a bit better, what these numbers mean. So here is 1 by 1, here is using 2 by 2, 10 by 10, and 5 by 5 seems to be working the best on this particular like task. And I guess this is not that surprising. So the better the semantic segmentation you do initially, so FH obviously has better. So as you can see on the x-axis, this means that the overlap between the masks that this method found is way higher to the GT, which is obviously 1, because by default GT overlaps completely with itself. That's why we have 1 here. And these methods have even smaller overlap, which means they are of lower quality. So that basically means the higher the quality of your segmentation masks, the higher the detection accuracy. And that's kind of, I guess, intuitive, but it's nice to have a chart like proving exactly that. Okay. They did a couple more ablations of pre-training, this time on Coco instead of ImageNet, and they still outperform the supervised and the SimCLR like baselines. That's the point there. Finally, they show that using GT labels, which kind of makes sense, helps them even increasing the pre-training image resolution, and always testing it on this resolution consistently improves the performance when we're using GT masks, whereas when we're using FH, the performance does not improve with resolution. Which I guess makes sense. They mentioned that somewhere here in the discussion portion of the paper. So okay, this part, how can this be? So one interpretation is that other images give us clean negative examples because images in Coco depict different scenes. However, it appears that negatives from the same image provide a stronger learning signal. Blah blah blah. We're not pushing features from the same object apart. Positives from the same image are also at least as good as those across segmentations if again they're clean. We are not pulling together features from different objects. So basically, if you don't have perfect segmentation masks, that means you'll have overlap between classes, which means sometimes you're gonna be pushing away 2 feature vectors even though there is an overlap where those 2 vectors are formed from the same object. So that's not something you want to do. You want to push away different objects. You want to pull together the same object, and that's like a hand-wavy explanation of why you need better semantic segmentation masks. Okay, wrapping up this paper. The main idea again is usage of these segmentation masks in order to form a richer training signal. So whereas SimCLR will, in this example, we won't have any segmentation masks, we won't have any semantic segmentation masks, which means SimCLR will just be pulling together these 2 because they belong to the same image, whereas here we have a much richer signal because of the presence of semantic segmentation. So that's pretty much it for this video. If you have any suggestion for which repo I should do a code walkthrough of, let me know down in the comments. So I was thinking maybe Dino or some of those newer papers that came out. So if you have any suggestion, please let me know down in the comments, and I definitely read those comments and you can influence the next video. Other than that, if you found this video useful, consider subscribing and hit that notification button so that you can get notified the moment I upload a new video. I've noticed that only 10% of you have the notification bell on, and only 5 or 6% of you are actually receiving those notifications because your YouTube settings are set in such manner that you are not receiving them instantaneously. So yeah, definitely toggle on that notification button, and until next time, bye bye.